Hey everyone. Today I want to talk about something that I assumed was true about Unity Engine, but it's actually not. And due to this, there have been many times where I've struggled to make my code faster. To explain all of this, I want to start with a story about how I got into the place that I am now, right? Because I don't think everyone necessarily has kind of gone down the same path that I have. I'm also going to be using this website called Compiler Explorer to kind of help visualize and articulate these ideas for those who might not be too familiar with these ideas. And I'm also actually going to be using the C language, though because the syntax is similar between C and C sharp in this case, hopefully these, if you've never coded in C, you can kind of like carry across some knowledge from C sharp and understand this one way or another. But I'm going to try to keep this something that even beginner programmers or people who might not understand certain things like this, hopefully y'all can still understand it to some extent. But I want to start with talking about my experiences with programming in high school. So in high school, I learned Java, and my teacher at the time basically told me about these concepts when it comes to functions, right? And that when you call a function in code, that there's this function call overhead, as it was named, as it was labeled. And the idea was that whenever you create a function, or at least the rule of thumb, the principle, was that you only wanted your functions to be really long. You didn't want them to be really short like this. You wanted them to be long, and the reason why is because every time you called a function, there was some air quote function call overhead that was required to facilitate the calling of the function. But in my Java classes, the teacher would tell me about this idea of function call overhead and its relation to performance. So what do I mean by this? So in this case, you can see here in this example code, I know this doesn't really make any sense. It's just a toy example. But you have this very small function. And basically what my teacher was trying to tell me was that having small functions like this are not good for performance, especially if you are executing these functions over and over and over many, many, many times in a loop or in just some, condensed part of your code where, it's going to be happening very often, right? The idea and what function call overhead really means is that when you call a function, the computer has to do this kind of internal stuff. It has to do this extra work in order to facilitate the calling of the function because it's actually jumping to a different place in the program code, executing, and then it has to return back to where it left off. Okay. And I took this notion and I said, okay, well, all right. So what you're saying is that uh, small functions are bad. I shouldn't have small functions. And I should only have large functions, functions that have tons of stuff going on inside of them, monolithic functions where a bunch of things are happening. Because what that means is that the ratio of the work that the function is doing in relation to the function call overhead will be smaller, and therefore, if it's done repeatedly over and over and over, it means that it's faster, or at least it's more performant. Those two things mean the same thing, but you get the idea. So I took this to heart, and I found this very disappointing because what it basically meant is that if you needed a function to be small, if it made sense in your mind, well, you had to manually inline it. Okay, what you had to do is you had to take this function and you basically had to copy the code and basically put it, you know, like this, essentially. You had to inline it like this, and that would basically eliminate the function call overhead. But what this ultimately means is that if in your code you're trying to, you want this function and you're calling it in a bunch of different places, you're doing this similar code in, say, 20 different places in your code base, and let's say there's a bug related to that code, then, maybe the bug is that you meant to do this for whatever reason. I don't know. It's just an example. Well, then you'd have to change that in 20 different places rather than just changing it in one place, for example. Okay. And so for many years, I just, said, okay, well, yeah, I have no idea how much this is impacting the performance. I don't know if it's slowing the computer to a halt. I didn't really know that. So I just took this information blindly without really looking deeper into the situation. And I will say, as a side note, I probably haven't learned my lesson, but I do spend more time researching, which is very important. But anyway, so after many, many years, I would say up until the point of working on Below the Stone, our video game project, at some point, someone else told me something that I kind of wish that I at least assumed from the beginning, which is that a lot of compilers nowadays automatically do inlining. So what that means is you can write functions however you want to write them, right? Design your code the way that it makes sense in your brain, and you don't have to worry about the trivial, the obvious, the minutia of like, oh, I have to manually inline. I don't have to worry about that kind of stuff. And I thought that was such a relief to hear that. And then many years later, I discovered this website that you see in front of you called Compiler Explorer, which allowed me to very easily see for myself what exactly is going on when you write code. And in this case, I'm going to use C code. Of course, there's other options. There's even C sharp, but I'm going to go with C because I think this really just shows my point. Okay, so this is some C code, and it's not meant to be anything realistic. I'm just giving you an example. And so you can see here, this is the C code, and this is machine code, or actually it's assembly code, but for the sake of simplicity, machine code and assembly code are basically the same thing. They're interchangeable, but they're not one-to-one. They're not exactly the same, just to be clear. But this is more or less machine code. This is more or less what the computer is actually executing. And what's cool about this website is you can actually, mouse over the C code and see which instructions kind of correspond to what. And so you can see here actually this red, blue, and orange, and if you highlight them, it corresponds to these, and these things called mov, or it's actually move. And so what move basically just means is you're moving data, you're copying data from one place to another. And as you can see, sensibly enough, you can see here this stuff, which I'm not going to explain. This is a memory location. All you need to know is this is a memory location. And this is the number 1. So you're taking the number 1 and moving it to this memory location. And that memory location is X, right? As some of you may have been told before, you can basically think of a variable as a representation of a place in memory, a place in RAM. And we have 3 of them, 1 for each of these variables. And then we have a bunch of other logic here. You can see we have a for loop, and then we have some stuff inside of it. So if I mouse over this stuff, you can see the stuff inside the loop. And then if I just put my cursor on the loop itself, you can see it's highlighting some stuff surrounding it and some instructions, which essentially what they're doing is basically saying continue to do this logic until some certain condition is met, and then we continue down. If the condition is not met, or if it is met, or whatever, then we're going to jump, JMP is short for jump in this case, all the way up to the top, and repeat this over and over and over until the condition is met, and that's it. Oh yeah, let me also put this back. Let me put this back. I meant to have this here before. And if I put that back, interestingly enough, you'll actually see something change here. But after the loop, you can see here we have, loop where we're just doing some random math, and then, XYZ, and then we're saying, okay, take our XYZ values and then add them together. So we're calling it inside the XYZ function. And as you can see here, we have, this is basically this whole thing right here is the actual function call, right? This is why we have higher level languages, because it means that you can do a thing that would normally, that normally would be done in 5 lines of code is now done in 1 line of code. Makes things a lot easier to read. But as you can see here, this right here, if I highlight this, it's the same thing as what's up here. So this whole dword ptr rbp minus 8, that right there is the x variable. This is the y variable. And this is the z variable. Okay? And so we're storing these in these kind of things called registers. And then we're executing basically the function using a special instruction called call in this case. And then at the very end, what we're doing is we are saying EAX, and we're taking the value inside EAX and storing it here. So basically what that means is, in this case, EAX has the answer to the add3 function. We're plugging in XYZ into this function, and the result is going to be stored in the result variable. And that's precisely what's going on right here. Okay. Now, all right, well, this is, so just to be clear, this is what I mean by the function call overhead, right? You have to basically do all of this. You have to execute this special call instruction, which what it effectively does is it jumps to this label right here, add3, which is actually this right here. So it basically goes from here to here, executes all of this code, which, as you can see here, here's the 2 add instructions, add. You're just doing 2 additions, essentially. But you have all this other extra stuff happening before it, right? So if this was something that was happening in a loop, you have to do all of this extra work just to add two numbers together. And it's going to slow your program down immensely, right? And so I didn't like this. And I said, okay, well, assuming that this is always happening, let me manually inline. Let me do this, X, Y, Z. And if you look over here, what you get is the code gets shorter. Okay, so what you now have is we are now taking X, putting it into EAX, and then we're taking Y, and we're adding it to EAX. So EAX is just our result value, our result register. And then we're taking Z, and we're storing it in EAX, or we're adding it, we're adding it to EAX. And there you go. So after these three instructions execute, you have the result of XYZ in EAX. But then, of course, it gets stored back in R, same stuff as before, blah, blah, blah. This is not really needed. There you go. So, yeah. And this, again, not to repeat myself too much, but, this was the thing that kind of bugged me for a long time. And then I was told, like I said before, that compilers take care of a lot of this stuff for you. Because of the decades of compiler development going on, it is now pretty much standard, at least for C and C++ compilers, to manually inline, in a vast majority of cases, functions that are very small like this, okay? They might not do it for big functions, but they'll definitely do it for small functions, which is important. Obviously, this add3 function is kind of silly, right? It's like, why would you ever need this? But this is very important when it comes to vectors, right? When you're creating vector types in programming languages, like if you do something like this, right? And you need to add two vectors together, well, you're basically taking the x's and adding them, the y's and adding them, and the z's and adding them together. You're doing a component-wise adding the numbers together. And obviously, if you were to have a function like that to add two vectors together, it would be inherently slow because it's a simple function. It's just adding numbers together. So you need that inlining. You really do need it. But with that being said, let me actually get to the point that I want to show you here. So you're looking at all this thinking, okay, well, it looks like there's overhead. What are you talking about? Well, the trick is that you actually have to tell the compiler that you want to optimize the code. You want to turn on the optimizations. But in this case, all I have to do is type in -0 or O, capital O, and then a number corresponding to the level of the optimization. There's actually different levels. I like to go with 3 just to make sure I'm getting all of them. So you put in this, and it optimizes your code. In fact, it optimizes it so much that it doesn't look like there's anything happening here, right? This is the main function, and the only thing in here is this thing called XOR EAX, which what this does is it just takes EAX and zeroes it out. So what that actually is this right here. All of this other code is gone. It doesn't exist. And you might ask why? What if you want to get this result? How do you do that? Well, here's the thing. Modern compilers are so good at optimizing, at doing trivial optimizations, that it just realized this isn't really being used anywhere. This computation isn't being sent anywhere else. And so it can just omit it. It can just completely remove it. And I think that's really cool, but it's also tricky if you're trying to benchmark your code, right? You want to see how fast or how slow this is or whatever, right? So what you could do is there's a lot of different things you can do. So the one thing you can do is make this variable global. And in this case, I'm using Clang. I think it changes depending on what compiler you're using. If you don't understand what I mean when I say that, don't worry about it. But in this case, I'm going to make my result variable. I'm going to put it out here to make it global. And this is what we get. So here, we can see it changed. But what we have here is now a move instruction. And it just says, dword pointer RIP plus result. So we see that result word, which is our variable. So it's storing something in result. And you can see the number 273. Well, what is that number? Well, actually, that's the result of all of this computation and this right here. All of that happens right there. Okay, so what the compiler has done is it has realized, hey, I know what the answer of this is, so I'm just going to compute it and then have an instruction that just takes that result and stores it, right? Because that's all it has to do, right? It's assuming that this result variable could be manipulated from external sources, or it's going to be accessed by external sources, and therefore it leaves this in. It still adds the instruction. And I think that's amazing, because it means that you can just write the code the way you want to write it, and the compiler will try its very hardest to make it as fast as possible. And you only have to worry about optimization when it comes to the less trivial stuff. And that's what I love about programming. What I love is that you get to solve hard problems, not solve easy problems. If you wanted to solve easy problems all day, you wouldn't even need computers. We would still be doing math on abacuses, abaci, however, whatever the plural is, right? We'd still be doing that. But the reason why we have computers is because we as human beings want a challenge. At least that's what I think. But anyway, not to get too emotional about this kind of stuff. So how does this go back to Unity Engine? I've been ranting for probably way too long now. What does that have to do with Unity Engine? So, Unity Engine is C#. They use C#. But the compiler / runtime that they use is called Mono, M-O-N-O. And I assumed, because I assumed Mono was a modern compiler, that it was doing all of the things that you see here, right? But it's not. And recently I did some benchmarks that were very simple benchmarks, but I should have done these benchmarks a long time ago. I should have done these tests and proved it for myself, but I assumed that, well, what was happening or what I thought was happening was actually happening. So with that being said, allow me to take a second here to move over to Unity Engine and show you these benchmarks and hopefully also amaze you with the stuff that I also didn't realize. Okay, so here I am in Visual Studio, and basically the focus of what I want to explain here and what I want to show is this very basic benchmarking code that I wrote. In this case, we're actually doing 3 different benchmarks. This one, and this one. I also want to preface myself in saying, yes, I know there are probably better ways to do this. I wanted to do something very simple, made it very easy and clear to compare the results of 3 different benchmarks. I know that there's a profiler in Unity Engine. That I didn't really feel was the right thing for what I'm trying to do here. I want to make the code simple to test these results, or to test the code and get clear results. So I have basically a loop. In the first test, I have a loop that runs, in this case, 10,000 times, and I'm basically taking randomly generated numbers, and I'm using them to compute a lerp 10,000 times. In the next one, I'm basically have the same loop, but there's nothing inside of it. So if you remember what I was explaining earlier about how in languages like C and their compilers, if you just have an empty loop doing nothing inside of it, well, it doesn't do anything. So the compiler could just completely remove this code and leave you with nothing, right? Because it's not doing anything in reality. It's not, the result of this loop happening isn't transmitted somewhere else. It's redundant, if you will. And this third test is a control test. So it's basically doing nothing. It's what we call a no-op, I suppose. In fact, even in machine code, you have a no-op. But in this case, I'm basically just starting my stopwatch, stopping my stopwatch without anything in between, other than this comment, which doesn't change anything. And so I can use it as kind of like a ground level to see, like, okay, if this is indeed getting optimized out completely and nothing is happening from here to here, then the result here, this timing result, this benchmark result, should be the same as this one. If they're different or significantly different, then we'll see that, and that will conclude that this is not being optimized out, even though it technically should. And the same thing can be said for this, right? One could argue that, well, we're taking this result and putting it somewhere, but the only result that matters is the last one. If we're just going through this loop and overriding this variable, the only value that matters is the last one. So if anything, the loop should be completely optimized out, and you'd only be doing one lerp. So that would mean that really this code should be really, really fast because there's no loop happening, but there is something happening, right? And basically the timing results should explain, or should show, I should say, what is actually happening behind the scenes. I also want to just say before I show you the results that, if you think that I could be doing things a better way in terms of benchmarking or analyzing or testing or whatever when it comes to stuff in Unity Engine with performance, I'd like to hear about it in the comments because I don't know everything. I'm ultimately just sharing my experiences with programming in general, and in this case in Unity Engine and C#, because I just like sharing my knowledge. So these 3 results are here. So I already have it running. Also, I don't know if I said this, but yes, I am in release mode. It says debug mode there, but I'm in, mode release. I'm in release mode right now. And from the testing that I've done in the past, making a build of the game and running this test gives you the same results as if you were just to, go into release mode and run it in the editor itself. It doesn't make a difference. If it does make a difference on your end, I am curious to see what you did differently. Also, I'm not using IL2 CPP in this case. If you use that, you definitely get a difference. But in this case, I'm focusing more on mono in this case. So you can see here the three results. You have and this isn't really a specific unit of time. This is just ticks. That's what the stopwatch is using in this case. And for the first result, we have something around 1,900 roughly. For the second one, we have about 30. And for the bottom one, the one that's doing nothing, we have 0.4, 0.5, somewhere around there. And in case you're wondering, well, why is there still a time for the no op? Well, it's because obviously there is overhead. There's probably going to be some delay from when the timer actually starts somewhere inside of this function to the point where it actually gets stopped, right? There's probably some error, and that's precisely why we do this test, to see what that minimum number is. So this is the kind of minimum number. And in this case, you can see clearly that 30 is a lot different than 0.5. So clearly, this loop, which has nothing in it, takes 30 ticks, approximately. Right? And when you add in this function here, this lerp unclamped, it then takes 1,900 ticks. And then you can do some math to basically say that, if you take this number and divide it by this number, you can say, oh, this thing is so many times slower than this other thing because it takes a lot more time, essentially. A bigger number means it takes longer, ergo, it's slower. And yeah, that's pretty much it. I could also show other things, like if you were to manually inline this function, and that's kind of what I was doing down here, as a matter of fact. Like if you took this and put it here and inlined that whole entire thing, what you'd find is that this number would be very small. I forget what number it would be. I don't know if it would be like 300. It'd be different for you, depending on your hardware. But in my case, it's this, and if you manually inlined it, it might be something like 300 or 200 or whatever. But also, if you make your own lerp function like this, and not manually inline it, but call this instead, you would get a higher result. So that kind of tells me that, okay, yes, like I was saying originally, in this case, mono is, for whatever reason, not doing any manually inlining in this particular instance. Maybe it does it in some other instances. Maybe it does it if you were to write this code like here and then down here. If you were to write this code twice, maybe both of those results, maybe one would be smaller than the other. I don't know. I haven't tested that yet, which I probably should. But this video is getting really long as it is, probably. So yeah, that's pretty much all I wanted to share. Is just I assumed, and this is the takeaway here, is that I assumed that all of these optimizations were happening, meaning that really all three of these numbers should be the same, or really these two numbers, that this one and this one should be the same, but they're not, which tells me that certain optimizations are not happening. To a greater extent, even this number should be a lot smaller, because in reality, this whole thing is doing a lot of redundant work. In reality, you should just be, plugging in, let's say in this case, the last number in this array, which would be, I believe, 9999. So you'd plug in 9999 in all these places, and then do that, and that would be a result. And it would be way faster. In fact, it would probably, oh, that's my alarm, sorry about that. It would be way faster, I think, than even this, because you're not even doing a loop at that point. It would be less than 30. But yeah, anyway, that's what I've learned. I think this video is probably long enough as it should be. But yeah, so I appreciate all you for listening. I understand that, these long videos are kind of boring and whatever. I try to remove all of the pointless things while also sharing all of my stories and experiences that I want to share. So if you don't have the patience for these long videos, I'm sorry, this is not the content for you. I try to make things as condensed as possible while also just making it interesting. So I guess if you don't like these videos, you also don't like, what's the word I'm looking for? What's on Spotify? What are those things? Podcasts, that's what they're called. I couldn't think of that word for some reason. But yeah, if you don't like, these long form videos, you probably also don't like podcasts. I'm sorry. But with that being said, thank you for those who do like this video. and would like to hear more of my rambling, then be sure to like the video, subscribe, and stick around for more of this programming obsession goodness. All right, so thank you guys, and I'll see you in a different video.